spectra were being studied in the beginning of sometime in the mid-1800s, and physicists and chemists were looking at different types of hot gases. They would just burn things and look at them through a prism or a diffraction grating and see these colored lines, and they were trying to make sense of it. And it turns out that that those things are best understood in the context of the atom, and that wasn't figured out until 50 or 60 years later, in the early 1900s. And so to understand spectra, we need to understand a little bit about the structure of the atom. Spectra give us information about the atom. And so the atom was first conceived a long time ago by various people, but it was really seriously understood in the early 1900s, beginning with Einstein. And so we're going to just talk for a minute about the structure of the atom. We understand how atoms work through the theory of quantum mechanics, and quantum just means a certain amount, a fixed amount. That's all quantum means. And so it means the mechanics of fixed amounts, and that's how atoms work. Quantum mechanics is probably the most tested theory in science. It's extremely well understood. Your cell phone has a few billion transistors in it. These are solid state objects that depend on quantum mechanical interactions to work. And if we didn't understand how those interactions work, we wouldn't be able to build these cell phones that work so well, or work pretty well, shockingly well. So billions of transistors interact in your cell phone. You can contrast that with a gas engine, which has about 2,000 interacting parts, or an electric motor, which has about 20. By the way, you're going to see more and more electric motors in your life, and the reason is because they're so simple. It's a tiny number of parts in electric motors. They're big motors and little motors operate on almost the same principle, and you'll see them more in cars and in everything because they're so simple and easy to use and don't break very easily. And so that's just a digression there. So we're talking about atoms. I think you know a lot about atoms already. Atoms are composed of three basic particles. They're called protons, neutrons, and electrons. The electrons are negative and kind of negatively charged and orbit the nucleus. The protons are positively charged and lived in the nucleus with neutrons. The neutrons are neutrally charged; they have no charge, and they're just adding mass to the nucleus. The number of protons in an atom is called its atomic number, and it determines what element it is. So hydrogen has an atomic number of 1 because it has 1 proton. Helium has an atomic number of 2 because it has 2 protons. Lithium has an atomic number of 3 because it has 3 protons. Beryllium has an atomic number of 4 because it has 4 protons, and so on. I think it's boron, carbon, nitrogen, oxygen, fluorine maybe. And so the atomic number just tells you how many protons there are, and that tells you what element it is. Two atoms with the same number of protons but a different number of neutrons are called isotopes. They act the same chemically, but they still have a different mass, and so they're slightly different, but their chemistry is the same. If an atom has a different number of electrons than protons, it's called an ion. If it has extra electrons, it's a negative ion. If it has too few electrons or a smaller number of electrons than protons, it's a positive ion. And so let's talk a little bit about how electrons are arranged in atoms. Well, let me just go back and look at these pictures for a second. So if I go over to here and here, and then I page down. Early experiments were on atoms and how they work were done by a lot of people, but Ernest Rutherford was one of them. He was from, I think, New Zealand, and he was shooting alpha particles. An alpha particle is just the nucleus of a helium atom. It's got 2 neutrons and 2 protons. And he would fire them at gold foil, and they thought the atom was just kind of a smeary object, and that these alpha particles, which are super tiny and massive, like little bullets, they thought it would go right through, but they found out that they don't, that some of them would bounce straight back from the gold foil, and that that told Rutherford that the mass of these atoms in the gold was concentrated at its center, and it led to a model that you're probably already used to, which has the mass of the atom and the nucleus in the center, as we see in this picture, and the electrons orbiting around that center. And so that's sort of the picture that even today, even though it's not super accurate, it is true that the mass, the neutrons and protons are at the center, and that the electrons orbit around it. Their orbits aren't really planetary, the way you would think of planetary orbits. They're more in a cloud, but that's the picture. If you scaled an atom up to the size of a football stadium, the nucleus would have 99.8% of its mass. Percent of the mass of the atom, 99.8% of the mass of the atom is in the nucleus, and it would be a dime at the 50-yard line. So it's a super tiny nucleus compared to the size of the rest of the atoms, the size of the cloud of electrons that are surrounding it. So what you see in the picture is a hydrogen atom. It's got one proton and one electron. And then here is a helium atom, right? It's got two protons and two electrons, and it's also got two neutrons in there. The most common isotope for helium has two neutrons. The most common isotope for hydrogen has no neutrons. And this gives you a little bit of the size scale here. This atom says 10 to the minus 10 meters. That's 10 to the minus 10 is 1/1 billionth. 10 to the minus 10 is the same thing as 1 divided by 10 to the 10, and 10 to the 10 is a 1 with 10 zeros after it. A 1 with 10 zeros after it is 10 billion, and so it's 1/10 billion, or 1/10 billionth of a meter. So a meter is a little larger than a yard. A helium atom has a diameter that's about a 10 billionth of that. And so there are the electrons orbiting around it. Here are some isotopes of hydrogen. The most common isotope is the one on the left. That's got no protons, one proton and no neutrons. The next one has one proton and one neutron. That's called deuterium. It's called hydrogen 2 sometimes because it's got two elements in its nucleus, two nucleons. Protons and neutrons are called nucleons because they live in the nucleus. And then tritium is another isotope. It's got one proton and two neutrons, or helium-3 it's sometimes called. Tritium played a big role in developing of hydrogen bombs in World War II in that time. Here are Niels Bohr and Max Planck, who also played a role in the development of the model the current model of the atom. And so let's just talk about this model as regards atomic spectra. And let me go back. I'll talk about this model just for a second, and then I'll go back to the text. So the nucleus, this is just a picture of the atom with these orbits going around it, right? The lowest orbit is n equals 1, and then the next one is n equals 2, then n equals 3, then n equals 4, then n equals 5. And a point at the center that you can't see is the nucleus. It's just a dot in the center, and you can't see it there. And so we would call the n equals 1 the lowest orbital, and the electrons that are in orbit want to get to the lowest possible orbital. So they want to get to the n equals 1, or if it's full, the n equals 2. You can think of these as rows of seats in an amphitheater. An amphitheater has the stage in the center, and the seats go all the way around it. And so there's a certain number of seats in the n equals 1 level, there's a certain number of seats in the n equals 2, and n equals 3, and so on. And so if you're looking for a seat and the front row is taken, you got to go to the second row. If the second row is all full, you got to go to the third row, and so on. Okay, and that's a decent picture of that. Now let's see if we can go to, oops. Here we go. Explain how electrons are arranged in atoms. Electrons orbit the nucleus in orbits that carry well-defined energies. The available orbits for electrons are restricted. Electrons cannot just be in any orbit. In order to move to another orbit, they have to gain and lose. They have to move to a higher orbital, to move to a higher energy level, to move to a higher row in your amphitheater. they have to gain energy. So the electrons have to absorb energy. To go to a lower level, they have to release energy. And so they can gain energy by either absorbing a photon or being bumped by another electron. They can release energy and go to a lower level. So step 3 is going to a higher level. Step 4 is going to a lower level by either releasing energy by emitting a photon or by bumping another electron. Emitting this photon is the way we see an emission spectrum. We get the atoms hot, knock them into each other, they bump into each other, the electrons go to higher energy levels, and then when they relax, they drop down to a lower energy level, emit a photon, and then we see it using our diffraction grating. In step 3, when they're going to a higher level, we see an absorption. They absorb photons. If we put those atoms in front of a continuous spectrum, they absorb photons out of that spectrum, and so we see an absorption spectrum. And so step 3 describes how we see absorption spectrums. Step 4 describes how we see emission spectrums. Any electron can only gain or release an amount of energy that exactly corresponds to the energy required to go to that other orbital. So from a 2 to a 3, or a 3 to a 4, or a 5 to a 2. And so this is why we only get certain lines of light from certain atoms, because their energy levels have specified differences, and those are the only ones that can be emitted. I think that's probably a good start there. The nucleus has a similar structure, but we don't talk about it very much. The only interesting thing about the nucleus, well, in the context of what we're talking about, is you might ask yourself, why do those protons that have like charges and thus repel each other stay together in the nucleus? And the answer is because there's another force at play called the strong force, which is stronger than that repulsive force, and that holds the nucleons together. Protons and neutrons attract each other when they're very, very close with a force called the strong force. And so let me go back and put the other pictures up here for a second. So so you can sort of see here, this is kind of a model for an atom. The nucleus is in the center, and electrons that are in high orbitals can fall to empty places in lower orbitals, and this little collection here called the Lyman series is all these electrons falling from higher orbitals to the n equals 2. The Balmer series is all, well, in this case, it's going from n equals 3 to higher orbitals, but it could go the other way also. And then the Paschen series is from n equals, so the Lyman is for n equals 2, the Balmer is for n equals 3, and the Paschen is for n equals 4. And that's just been redrawn over here on the right, which instead of curved lines, straight lines. And so you notice all of these lines have different lengths, and these different lengths correspond to the energy difference, which tells you something about the spectrum that you're going to see. Notice we don't have anything falling to n equals 1. It turns out that all of the transitions to the n equals 1 level are in the ultraviolet spectrum. We don't see those. So for hydrogen, the colors we see come from falling really to the n equals 2 level. And so that this little section right here, the Lyman series, is what we see. I'm pretty sure these other two guys are in the infrared. And of course, every atom has a different collection of these, and so they have a different set of flavors, different set of colors, different set of lines, and so we only see we see a different set for every atom we're looking at, and that's how we can distinguish by looking at the spectrum what atom we're looking at. This is really a beautiful piece of work that happened in the early part of the 1900s that explained those collections of colored lines in the spectrums that we were looking at, in the emission and absorption spectrums that they found in the 1850s and had really no good explanation for. So the last section of this chapter is on the Doppler effect. The Doppler effect was discovered by Christian Doppler, an Austrian, in 1842. He's studying binary stars, but it's widely used nowadays. You can experience the Doppler shift yourself if you hear a car with a siren going past you at a fast speed. When it's coming towards you, you hear a hee, and when it goes by, you hear woo. It goes ee. So you hear a high pitch when it's approaching you and a lower pitch when it's receding you, and that, in essence, is the Doppler effect. The waves get compressed as they're coming towards you because the source is chasing the waves as they leave, and that the effect of that is to compress the wavelength in the forward direction and to stretch it in the backward direction. So in the backward direction, when it's running away from you, you hear a lower pitch. In the forward direction, you hear a higher pitch. That's for sound. But light works kind of the same way. It's still a wave, and so an object approaching you, you will see a shorter wavelength than you would expect, and an object that's receding from you, you would see a longer wavelength than you would expect. And it turns out that if you analyze those carefully, how much longer or how much shorter the wavelength has been made by this effect tells you how fast the object is going. And so, for example, we've been talking about spectra. If a star has a hydrogen spectrum, but it's shifted, we can look at how much it's shifted, and that tells us how much the object is approaching or receding from us. Now, if it's moving perpendicular to us laterally, the Doppler effect won't help you with that. It just does forward, moving towards you or away. So when an object is approaching us, we say it's blue shifted. The light coming from it is shifted towards shorter wavelengths. In the visible light range, blue is the shorter end of the wavelength scale and red is the longer end of the wavelength scale. So if an object's spectrum is blue shifted, that means the object is approaching us. If it's red shifted, it's receding from us. And so it turns out we can just look at the Doppler shift. We can look at the spectrum coming from a star, and we can pull out the hydrogen spectrum or the helium spectrum. We can say, hey, wait a second. All these little colored lines are shifted a tiny bit. They're all there, but they're shifted a little bit. And from how much they're shifted, that tells us how much it's approaching or receding us. So I'll show you some graphs here. So on the left here is a fire truck that's stationary, but it's playing its siren. And you can sort of see these concentric circles. Those represent the peaks of the waves that are going out. You can sort of see each wave, the peak corresponds to the circle, and so the distance between those rings that are going out from the fire truck are spaced according to the wavelength of the sound wave that's being played. When the truck is stationary, the sound wave in all directions has the same wavelength. However, something weird happens when the truck is moving forward, because the truck is driving as it's emitting the wave, and so it's kind of chasing the wave fronts in the forward direction and thus making them shorter. And your ear perceives that as higher pitched. Similarly, behind the truck, the waves are stretched out, and you hear that as a lower pitch. A more general picture of that is this one up here. Maybe? We were just on this a second ago. Right? In this picture, and by the way, this works for light and sound. Since they're both waves, it works exactly the same for both. So in the picture on the left here, the source S is stationary, and in the picture on the right, it's moving. And so S1, the one that my cursor is on right now, that's at the center of the outer ring. It's now at position 2, which is at the center of the second ring. And then S3 is the center of the third ring, and S4 is the center of the fourth ring. And so you can see how these waves get emitted. The source, S, is just moving downward towards observer A, and so all the waves in the front are getting crunched, all the waves in the back are getting stretched, and the lateral waves aren't being changed at all. The wavelength to observer, so A is in the forward direction, B is in the lateral direction, and C is in the backward direction. And so when an object is moving in a direction perpendicular to your line of sight, like you're over here for observer B, but the source is moving down the page, you see no effect from the Doppler effect. When you experience the Doppler effect, you're only experiencing a component that's towards or away from you. And so that's all the Doppler shift tells us. But it tells us if things are approaching or receding. So how does that manifest itself? How do we see that with light? Well, here's what happens with light. See if I can pull this one up. And so let's look at this absorption spectrum, just because it's nice to have it on the background of a continuous spectrum so we can see what's happening. Look at the top row. So the top row is when the source is stationary. And so you can see all these dark lines, this pattern of dark lines on the top row here, this absorption spectrum. It's the absorption spectrum you would see if the source was stationary. And now the source is moving. Imagine this is a star, and the dark lines are its atmosphere, so the atmosphere is moving with the star. Right? Well, if the star was moving away from me, then all of the wavelengths for each individual line would be redshifted, would be shifted towards the longer wavelengths. We call that a redshift because red is at the long wavelength end. And you notice every one of these lines is just shifted a little bit to the left from the ones for where it was stationary. And so we would call that a redshift. Notice the pattern is exactly the same. And so if this is a hydrogen, if we saw an absorption spectrum for hydrogen on a continuous spectrum, but it was all shifted a little bit from what we expected for one that was stationary, we'd say, oh, this star is moving away from us. How far it was shifted would tell how fast it was going. And so it's very easy to pull out these patterns and go, oh, this is a hydrogen spectrum, but it's shifted, so that tells us that its source is moving at thus and such a speed. Similarly, the bottom row is a source that's approaching us. It's blue shifted. It's got all the same absorption lines as the top absorption spectrum, but they're now shifted towards the blue. They're right shifted, right? And so we call that blue shifted. And so this is an object that's approaching us. And so the top object is stationary. The middle object is when it's approaching us at a certain speed. The bottom object, receding from us at a certain speed. The bottom object is approaching us at a certain speed. And how far they're shifted, we can use how far they're shifted to calculate how fast they're going.